We have transverse waves, where the distance of the medium is perpendicular to the direction in which the wave is propagated, so in which the vibration goes to. So here, let's think about water and the ripple effect. If we throw a stone into our water, what's going to happen is that the water, that stone is going to give the water energy to move up and down, up and down, up and down as the wave proceeds in this direction. So the wave is moving from our left to the right, but the medium is going up and down, up and down, up and down. So we can see that the waves are moving perpendicular to the vibration. Whereas we have a longitudinal wave that we can create with a slinging. So if you push a slinging to the right, the slinging would go to the right, and the pulse is also going to the right. So we can see in longitudinal waves, we will have waves that are moving parallel to the direction of the pulse. So they've given us examples of transverse waves. We have water waves, electromagnetic waves, and with regards to longitudinal, we have sound waves, and they also used a slinky spring just to explain the longitudinal. So the next thing we're going to focus on is the properties of waves. The medium of a wave is going to move up and down, up and down with regards to a position that we call the equilibrium. This is the resting point of the medium. So there will be a displacement of our medium up and down, up and down. And the maximum displacement from the point of equilibrium or from the point of rest is called the amplitude. Then the distance taken for our wave to be in phase again is seen as the wavelength. A complete wavelength, get the time taken to complete a wavelength, we're going to call that a period. And if we look at how many waves pass a certain point, we are then looking at the frequency of our wave. So with regards to equations, we need to know when it comes to waves, these are the formulas that you would need to know, and you would also find these formulas in your formula sheet. My number one thing to do when I'm studying is always have my periodic table or the information next to me, the information sheet next to me at all times. So I understand how to use it when I get into my exams. I know where all the different topics are placed, and I know how to use each and every equation on my formula sheet. So here we can see the relationship that exists between the period and the frequency. We see that the period is equal to 1 over the frequency, and that the frequency is equal to 1 over the period. We also have an equation to calculate the speed of a wave by multiplying the frequency with lambda. Lambda here is the wavelength. Please note that these are the units that we're going to use when we are calculating with regards to waves. So with regards to waves, looking specifically at the electromagnetic waves, this is now our transverse waves. I want to show you an image. Give me a second. So in terms of the electromagnetic waves, we have different electromagnetic waves depending on either the frequency and the wavelength. So let's start here where we have our longitudinal waves, our infrared, our radio waves, our microwave, right? We can see here that when we look at the frequency, we would have a low frequency but a high wavelength. And as we move along, going all the way to gamma and the ultraviolet, we can see we will have high frequency, but a low wavelength. Now, when it comes to the Doppler effect, our eyes would focus on this part of the electromagnetic spectrum, which is known as, over here, which is known as the visible spectrum range that goes from a length of 700 to a length of, from 400 to a length of 700. Okay. Now, the visible spectrum is made of different colors. So the visible light spectrum is made of different colors, starting at red, going all the way to violet. Now, what is the difference between the colors with regards to their energy, their frequency, and their wavelength? We will see that at red, we have a very long wavelength, that is accompanied by low frequency and low energy. You also have to remember this for photons. And when we look at the violet side, we will see that they have a long wavelength, but this is accompanied by a high energy and high frequency. So you have to keep that in mind when we now look at how the Doppler effect affects light and how we can use this application in real life. So let's talk about what the Doppler effect. The Doppler effect is the change in frequency or pitch of a sound or the color of light that is detected when the wave source and the observer move relative to one another. So that implies that we're going to see a change in frequency depending on whether we are moving towards an object or we are moving away from a certain object. Now, first we're going to look at it with regards to light and sound. And when it comes to sound, the questions are going to be application-based, they're going to be calculation-based. Whereas the questions that come with light are going to be theoretically based. So it's important that you understand the Doppler effect with both regards to the light and to the sound. Now, for the sound, is a little bit better to understand because we can visualize it. You can see we have a truck that is moving, and the truck is a source of the sound. As it approaches the person standing here, the waves that are coming from the source of the sound become smaller. And we know once they become smaller, it implies that we're going to have a higher frequency. So it is important for us to understand that frequency and the wavelength are inversely proportional. When one is high, the other one is low. And when the other one is low, the other one is high. So because we have a much smaller wavelength, we are going to now experience a higher frequency. And the person who now hears this truck coming through is going to hear a very high-pitched sound. Then over here, we're going to have the truck source the sound of the source is now moving away from the person. So the wavelengths that gets to this person are much larger. This implies that we're going to have a lower frequency and the person will hear a lower pitch. Now we have expressed that with regard to an equation over here. So here they're trying to create a ratio that the listener is going to hear in terms of frequency with regards to the source. All right. So when the truck or in this case, whatever sound source is moving towards, towards the person, or at the top, we're going to add, and at the bottom, we're going to subtract, right? It should make sense because we want a lower ratio between the two as it's moving towards, or actually a higher ratio between the two. So we want the number at the top to be bigger, and we're going to have the number at the bottom be lower. In this way, we will get a bigger ratio. Therefore, the listener is going to hear a frequency that is actually going to be higher than what the source is emitting. Whereas now, if the person is standing, or if the sound of the source is moving away, then what we want in terms of the ratio that's going to now exist between the listener and the source, we want that ratio to be small. So the only way that's going to happen is if the number at the top is small and the number at the bottom is big or large. And that is why we are now subtracting at the top and we are adding at the bottom so that that ratio is small. So if we want to think about it with regards to numbers, it should be something like a 5 out of 2, where this should be something like a 2 out of 5. So now another way we need to look at it is with regards to your light. So we saw that when it comes to the visible light spectrum, the color that is emitted and the frequency we have must, in a sense, correlate, right? We said if we have a red light, then we know that we would have long wavelength and a high frequency. And if we have a short wavelength, then we're going to have high energy and high frequency. Now, let's tie that in with the Doppler effect. So we already understand that the electromagnetic spectrum has a full range of electromagnetic radiation. We talked about the microwaves, we talked about the infrared, the gamma rays, and so on. But what we are interested in is the visible light spectrum. Now, they use the Doppler effect to determine whether a star in space is moving towards us or away from us. So, stars, like the sun, emit light. When a star moves away from the Earth, its spectrum shifts longer waves. In other words, the red side of the spectrum. The star appears to be red when we look at it. Next. Whereas when a star moves towards Earth, its spectrum shifts towards the higher frequency, and then it appears to be blue. So these two statements that you have here are the two that you would need to remember for your exam. When it comes to Doppler effect with light, that is the only two questions that they will ask you. They will ask you what is a redshift or what is a blue shift, or how do we use the understanding of wavelength, frequency, color in terms of determining if an object is moving close to us or moving away from us. They could also give you a question where they said, oh, someone spotted a star and the star was red. Is it moving away or is it moving towards us? And explain your answer. So that's the typical exam question. Let us look at an exam that they did in 2024. So basically everything we have covered at this moment is everything you would need to know when it comes to the Doppler effect. It's a very short part of physical science. This is a question that was done the year 2024, last year, in the November past papers. It says a stationary listener standing on the roadside records the wavelength of the sound emitted by a siren of a police car traveling at a constant velocity. In the wavelength time graph below, not drawn to scale, no, that's not a problem. The wavelength, lambda L is the wavelength of the sound recorded by the listener, and lambda S is the wavelength of the sound emitted by the siren. Take the speed of sound in the air to be 343. 6.1, it says name the phenomenon that explains why the wavelength shown in the graph is different. Yeah. So here they want to see if you understand the definition of the Doppler effect. Okay. So you can see that the person has registered a different wavelength than what the source is emitting. And we can see that is due to the Doppler effect. 6.2 wants to know, is the car moving towards or away from the listener? Give a reason for the answer. So let's think about it. We said that when the truck is moving towards the listener, we are expecting to have a frequency of the listener that is greater than the frequency of the source. And this would then mean that, because we understand that the relationship between frequency and lambda is inversely proportional, then that would mean that the frequency or the wavelength that reaches the listener is less than the wavelength of the source. Now, if we look at the two values, we can see that the wavelength of the listener is greater than the wavelength of the source. So it means it's opposite of what would have happened if it was moving, towards. So if it was moving towards it, we know that the frequency that the listener hears must be greater than the frequency of the source. We know that the frequency is inversely proportional to our lambda. So this means that the lambda of the listener would be then less than the lambda or the wavelength of the source, which is not what we see here. What we see here is that the lambda of the source of the listener is greater than the lambda of the wavelength in this case of the source. So the listener is greater than the source. So then we would say it was moving away from the listener. Then 6.3.1 says calculate the frequency of the sound emitted by the siren. We can use V is equals to the frequency multiplied by the lambda. The reason why we would use this equation is because we are given lambda. We know the speed of light in the air, and the only unknown is the frequency. So we can change the equation to make the frequency the subject of formula. Substitute in our value, 902,63 hertz, or you can write per second. It depends on what you want, per second. Then it says 6.3.2, the magnitude of the velocity of the car. So in this case, we're going to use our equation here. We have the frequency of the listener is equal to the frequency of the source. Here, because we say it's moving away, we have the velocity of the air minus the velocity of the listener, velocity of the air again minus the velocity of the source. The listener was stationary, so we already know the velocity of the listener is going to be 0, right? Stationary. Okay. I personally would rather fix the equation before working with the equation. Okay, so already I know that the listener is equal to 0 because the listener was stationary. So I have V over V minus Vs. I'll take my f of s to the other side, and I'll have V over V minus Vs, of which I need to multiply with V minus Vs on both sides. Okay, so now I have V over Fs minus V S Fl over Fs. These two cancel out. I have V by itself. I now need to move this V to the other side. So I have negative Vs Fl over Fs is equal to V minus Vfs over Fl. And I'm going to go ahead and divide or multiply by the inverse, multiply the whole thing by the inverse, then not just the inverse, I need to get rid of that negative, so that negative goes away. So then my Vs would be V minus Fs over Fl multiplied by V and multiplied by negative Fl over Fs. It's Fs over Fl. There we go. Oh, so this is upside down. My apologies. So the velocity of the source would be equal to 343 minus the frequency. We only calculated the frequency of which value did we use of the source here. We now need the frequency of the listener. So FL would be 343 divided by 0.4, which is 857.5. 857.5. Now we have the frequency of the listener over the frequency of the source multiplied by a negative frequency of the source divided by 8575. Fixing it can be, oh, that was supposed to be a positive, so actually there's no negative. The bottom part is supposed to be a positive, my bad. Then we would get an 18.05 meters per second as the velocity of our source. So yeah, the tricky part here is having to rewrite the equation, make sure that you do it correctly. And also putting in that VL as 0 to begin with, I think it would make it, would give you a much faster process. Okay, then once you have it as your subject of formula, you can go ahead and substitute, and that's why the question was worth here 6 marks.